Welcome to The Explainer. Today, we are digging into some source material that completely shifts how we view machine learning. We're going to explore the exact statistical derivations behind loss functions. The whole goal here is to transition from merely operating machine learning frameworks to truly understanding them, right from the math up. If you've ever just blindly typed dot backward on a loss function without knowing exactly why that specific math was chosen, well, let's figure it out together.
All right, let's dive right into our roadmap. First up, we'll look at the disguise of loss. Second, we'll examine our main suspects, output distributions. Third, we'll run a little interrogation using maximum likelihood estimation. Fourth, we'll introduce a massive information theory twist. And finally, we're going to piece it all together into one unifying picture.
Okay, part 1, the disguise of loss, or unmasking your ML defaults.
So you know that illusion we all kind of fall for? We blindly accept coding conventions, like using mean-squared error for regression, simply because a framework defaults to it. But I really want you to absorb this quote from our source material. Every loss function you've ever called dot backward on is a probability statement wearing a disguise. It is not just some arbitrary equation somebody made up. It's a strict, undeniable mathematical consequence of what you believe about your data.
Seriously, think about it for a second. Why do you actually use mean-squared error for regression? Is it just because squaring the errors heavily penalizes the big mistakes? Is it because the derivative is super easy to calculate? I mean, sure, those are really convenient side effects, but they absolutely aren't the root cause. If your data behaved even slightly differently, MSE would actually be the completely wrong choice. To figure out why, we need to look at what's hiding underneath.
Moving on to part 2, output distributions, also known as the suspects.
We've really got to stop looking at probability distributions like they're just trivial checkboxes from a college stats class. In machine learning, naming a distribution is a highly active design decision. Just look at how cleanly pure statistics map right onto our everyday ML code here. The Bernoulli distribution, which is basically a single coin flip, is exactly what a binary classifier using a sigmoid activation is doing. A categorical distribution is just a multi-sided die, which perfectly describes a softmax layer, and the Gaussian distribution, that is the hidden assumption right behind your regression targets. Every single architecture makes a claim about distribution.
And this brings us to a core realization, which is honestly probably the most important sentence in this entire explainer. Choosing a distribution for your output is equivalent to choosing a loss function. The very second you name your assumed distribution, your loss function is no longer a choice you get to make, it is a derived mathematical certainty. Let's actually look at how the math proves this.
All right, part 3, maximum likelihood estimation, the interrogation. This is the interrogation phase, where we extract the true identities of our loss functions using pure calculus. So what is maximum likelihood estimation, or MLE for short? Simply put, it's the mathematical mechanism of picking the model parameters, the weights and biases, that make your observed data the most probable. When you're training a neural network with gradient descent, you aren't just metaphorically trying to find a good fit. Under the hood, you are literally just running maximum likelihood estimation. Let's actually walk through how this builds step by step, because honestly, it is like a deeply satisfying mathematical magic trick. Let's say you assume your regression targets have Gaussian noise. Step 1, you just write out the standard Gaussian likelihood equation. Step 2, well, multiplying a ton of tiny probabilities leads to floating point underflow, right? So you take the negative logarithm, which neatly turns those products into sums. Step 3, you drop any constants that don't depend on your model's parameters, because they just don't matter for finding the minimum. And step 4, look at what's left. It is literally just the sum of the square differences between your prediction and the target. You have arrived exactly at mean squared error. You didn't invent MSE, the Gaussian distribution completely mandated it. So now, what if we take MLE, which only looks at the data, and we bolt on a prior belief about our parameters before we even see the data? Well, that gives us maximum a posteriori, or MAP. MAP is quite literally just MLE plus a prior belief.
And this is wild, because it brilliantly illustrates where our regularization tricks actually come from. If you apply Bayes' theorem and say, hey, I believe my weights should be tightly clustered around 0 in a Gaussian distribution, the math spits out exactly L2 regularization, also known as weight decay. If you assume a spikier Laplace prior, the math hands you L1 regularization. Weight decay isn't some magical hack an engineer just guessed and checked. It is literally just Bayes' theorem applying a prior belief to your network.
Which brings us to part 4, the information theory twist, looking at things from a totally different angle.
We're going to examine these exact same concepts, but through the lens of bits and coding theory. In information theory, everything starts with entropy. Claude Shannon defined entropy as a measure of surprise, basically the average uncertainty baked into a distribution. If you have a totally rigged coin that always lands on heads, the entropy is 0. There's no surprise. A perfectly fair coin, though, has maximum entropy. In machine learning, low entropy means a highly confident prediction. This is the exact toolkit sitting behind techniques like temperature scaling in large language models or entropy bonuses in reinforcement learning that force an agent to keep exploring by penalizing overly confident, low-entropy policies.
Now, when we want to compare two distributions, say our true data versus our model's predictions, we use KL divergence. It's a measure of the extra bits wasted by using the model's distribution instead of the true distribution. But here is the kicker. Direction matters. Forward KL divergence is mean-seeking and mass-covering. It tries to cover absolutely everything, which is why standard generative models can sometimes produce blurry samples. Reverse KL divergence, on the other hand, is mode-seeking. It prefers to nail one specific pattern perfectly, which is why it's an absolute staple in variational autoencoders, or VAEs.
So here's the absolute crucial point to take away. KL divergence is really just cross-entropy minus the baseline entropy of the true data itself. But wait, actually think about that. The true data's entropy is a fixed, physical property of your dataset. It doesn't change when your model updates its weights. Because of that, taking the gradient to minimize KL divergence is mathematically identical to minimizing cross-entropy. That is exactly why we train classifiers using cross-entropy directly. It's the exact same operation, just computationally cheaper, because we get to skip calculating the data's fixed baseline entropy.
And finally, Part 5, the unifying picture, the grand reveal.
It's time for the grand reveal, where we bring both the statistical likelihoods and the information theory bits together into one single, undeniable truth. Let's just walk through this definitive cheat sheet together. If you assume your output data has constant Gaussian noise, maximum likelihood estimation gives you the sum of squared errors, which mandates mean squared error loss. If you assume Laplace noise, with those heavier tails, MLE gives you the sum of absolute errors, dictating mean absolute error or L1 loss. If your output is a binary coin flip, a Bernoulli distribution, you get binary negative log likelihood, which is perfectly identical to binary cross-entropy. And for multi-class categorical data, you get standard cross-entropy. The choice of likelihood mathematically mandates your specific loss function. They're all the exact same mechanism, just viewed through slightly different lenses.
I want to leave you with a final thought today. A bit of a challenge, really. After seeing how all these defaults, MSE, cross-entropy, weight decay, are rigorously derived from base probabilities and entropy, ask yourself, are you just operating ML frameworks, kind of blindly trusting the defaults? Or do you now understand them deeply enough to debug them under load, to tweak them when your data breaks assumptions, and maybe, just maybe, even build the next one? Mastering this statistical derivation isn't just academic box checking. It is for sure the fundamental bridge from user to builder. Thank you so much for joining me on this explainer. Keep digging into the math, and I will see you next time.